Number 12, an airplane descends from an altitude of 9,500 feet to 5,000 feet at a constant rate of 400 feet per minute. What type of function best models the relationship between the descending airplane's altitude and time? They love this kind of thing where they give you a word problem, and then these are your 4 options. What kind of function is it? Is it a decreasing exponential, a decreasing linear, an increasing exponential, or an increasing linear? It's always those 4 choices. So let's look at what those 4 graphs are. An exponential graph is going to be curved, and it's either going to be shooting, like one end's going to be going towards the sky or towards the ceiling, or towards the ground, not the ceiling. So if I were to graph these, it would look something, would be going like that. Or it would be, and it's not letting me undo, or it could be something like that, or something like that, or last option like that. Those are our exponentials. And if we're looking at them in equation form, it's going to be things like 2 to the power of x, like y equals 2 to the power of x. X is the exponent, exponential. Linear are just lines. They are things that can be written in the form y equals mx plus b, where m is my slope, b is my y-intercept, and, they're just lines. So the decreasing and increasing part, you're always going to look at this if you're going from left to right. Left to right is how we read in English. So as we're going left to right, if the graph is going up, then that is an increasing graph or increasing function. If it's going down, that's decreasing. So let's take our exponentials. If I have something like this that's going from left to right, it is going up. That's increasing. If it were like this, then as we go left to right, it's going down. We're going left to right across the graph. It's going down. If it is like that, and I drew that poorly, but like that, there we go. If it was something like that, then that as we go left to right, that's going down. If last variety is like this, then as we go left to right, it's going up. And it doesn't matter if, like in this case, it's starting to head up for the sky, or in this case right here, it's kind of plateauing and heading towards a limit. It doesn't matter. All it matters is, as we're going from left to right, it's going to be either going up or going down, no matter how big or small of an increase that is at any point. Now, for this particular one of the things to look for is like how things change. I got to add this in here. This is just for this type of problem, some helpful information. A lot of times people think of interest problems as being automatically exponential because they've probably heard that term, exponential growth. Compounding interest. Oh, that's exponential growth, compounding interest. While that is true, it does not mean that all interest is exponential or that the graph of that interest would be exponential. You have to look at it, is it a constant rate of increase or a constant rate of decrease, or is it something that's accelerating and getting faster or decelerating and getting, way slower? It's that kind of thing. So we can either look at the graph, we can look at the equation, or we can kind of look at the words that are used in here. The biggest tip-off on this one is a constant rate of change. Constant rate. This plane is not speeding up as it's accelerating. It's not accelerating as it descends. It's not going faster and faster. It's also not slowing down its descent. It's not going to level off. Like if it did like it fell out of the sky almost, but then, woo, it caught itself and now it's leveling off. That would be a decreasing exponential. And then it slowly started to keep going back down to the earth. It's that kind of shape. Like, how is it behaving? And that's what we're wanting to know, because it's the altitude and time. What's the relationship between altitude and time? There's my altitude. It's changing at a constant rate. It's going 400 feet down every minute. Every minute. 400 feet down. In the next minute, we're going 400 feet more down. In the next minute, 400 feet more down. So if we were to look at this plane in the sky, it would be going, it's a very steady very steady, 400 feet every minute. It is decreasing. The altitude is going down as we go further in time. So this is a decreasing function, and it is a constant rate of change. The slope is constant. Rate of change is another way that we can express slope. You don't hear it that often. Usually your teachers will call slope something like change in y over change in x, rise over run, but it is the rate, a constant rate of change. Those are words to look out for in the SAT. So this is a constant rate, 400 feet for every 1 minute. It doesn't change. That is a slope, a constant slope. It's going down. It is a decreasing linear function. We don't actually have to write out or figure out what the actual equation of that line would be. The fact that it is going down, the plane is descending, it's going down over time, and that we're told it's a constant rate of change. It's not speeding up or slowing down. Either of those would make it exponential, like it's really started to and it slows down, or it was really starting and it slows down, or it was starting and then it speeds up. I'm just making a mess of this, aren't I? Of that graphic. Any of those descriptions would indicate an exponential, but that's not the case here. Decreasing linear is my answer, B.